In the previous example, which is this one, we said that the weight matrix values we already knew. We assumed the perfect boundary with values 1 1. We already knew what the bias was. Now what we'll try and do is uh, say that we do not know what the decision boundary is, and we'll start out with some random values for w and see if we arrive at the optimal values for w that correctly classify the data points we are looking for. And so here are a couple of data points, and let's just first write them down, and we can then plot them in decimals. So the very first data point we have is p1, and this data point uh, has values 0 0, and we also have accompanying target, and the target class for this data point is 0. We put them in this sort of curly braces, and then the second point we have p2 is 0 1, and the target for this one is again 0, so that's the true class for that data point. We have another point p3, this is 1 0, and then the target for this is again 0, and so that's what we have there. And then finally we have the fourth data point, which is 1 1, and this is the only data point that is a target class, which is 1. And we can try and plot these points here. So we can say p1 is equal to 0 0, so that's our first data point. Then we say p2, that is 0 1, that's the second data point we have. We don't need that, so let me put a equal to sign in between there. p3 is equal to 1 0, and finally p4 is equal to 1 1. So p4 is equal to 1 1. So these are the data points we have, and just to make things simple, what we'll do is color them accordingly. So let's say if these are all uh, the same class, so we'll say that those are all blue, and let's change the size of the dots to 20. Let's change the size of this and all other dots to 20, and make them of the same color if they belong to the same class. And then we have this one data point which is uh, of the class 1, and so we color it differently, maybe something that stands out like this. All right, so with this, what our task now is to find a decision boundary that separates these classes correctly. And the challenge now is that we do not know what the decision. We definitely think that it's probably going to pass through something like this, maybe 1.5 1.5 like that. But let's see how we can approach it the way a perceptron would try and arrive at the correct decision boundary, or the values for w1, values for w. So to get started, what we can do is we can assume that our decision boundary in this case is, let's say, 2 2. So if we try and plot a vector here, so it's a vector w is equal to vector, and say 2 comma 2, uh, then and of course we need to give this starting coordinates as well, so we do that and then we do that. So that is our w. If we plot that, and let's say that we give it some other color so that it looks different, and then we can draw a line which is perpendicular to that. And to do that, what we can say is this is simply 2 2, and so our y-axis is, so we can use the ax plus by plus c is equal to 0. So as we can simply say 2 times x plus 2 times y uh, plus 0 is equal to 0, because we will pass the line through the origin, and so that is the perpendicular line we have. Again, we can change the color of that line to this, so that it's the decision boundary. So that is what we have, and clearly it does not work. The decision boundary that is passing through the origin like that, it is not helping us to of kind of separate this. So what we can do is maybe add a bias, and let's say the bias term we add is a value of -3. Now if you do that, well, looks like it does work. Now it does work. We do see that these are these points on this side are negative class, a is equal to 0. These are positive class, a is equal to 1, and that does seem to work perfectly. We can take a screenshot of this and maybe try and uh, calculate these some of this manually. And so what we have here is the weight vector, which is 2 2 in this case, and let's say if we assume that the decision boundary is intersecting x and y axis at this position 1.5. Let's say we assume that the value for p is 1.5 and 0. Then what we can do is we can plug this in the equation that we already know with the new notation 1 wt w transpose p plus b, and what this is going to be equal to 0, because that's the decision boundary. And let's say we are trying to calculate the value for b. In this case, the w, once we transpose it, would become 2 as a row, 2 2, and then we have to dot that with 1.5 0 plus b, and so this becomes 2 times 1.5 plus 2 times 0 plus b, and so this is 3 plus 0 plus b is equal to 0, and therefore what we get the value for b is -3. So here we can say that the b is -3 that we just calculated. With these values now, what we can try and do is see if uh, mathematically, if we try and calculate the value for a, do we get a is equal to 0 for these 3 data points, and do we get a is equal to 1 for this data point. And to do that, what we can do is simply again use our um, terms that we have used previously, which is the transfer function hard limb. In here we are going to use w. Let's say we are first going to calculate this data point 0, let's say 0 0, and that is our p1, then 0 0 1, this is our p2, this is p3, and this data point is p4. So for this we are going to again use the same setup, w1 wd transpose, and let's say we use p1 first, and then we add the bias term here. So what we get is hard limb, and in here we have the 2 2, which is the weight matrix, and then the values for p1 are simply 0 0 plus the bias term, which is -3, and so what we get is hard limb, and in here we have just the 0 plus 0 -3, and so what we are looking at is hard limb value of -3. Therefore what we get in the output for a is simply 0, and that matches what we have here. So this is on the negative side, a is equal to 0, so that checks out. Now let's look at another another class, which is, sorry, another data point, which is this one, a is equal to 0 p2. I'm going to write here a is equal to hard limb 2 2, and we have the point 0 1 plus -3 And if we try and calculate this, what we get is this is 2 times 0 plus 2 times 1 minus 3, and so this becomes 0, and then this becomes 2 minus 3 becomes minus 1, so we are looking at a value of hardly minus 1, and that again gets us a value of a is equal to 0, so this one also checks out. Next, let's look at a is equal to hard limb, and here we are going to look at point P3. So P3, this is 2 weight vector, there's 0 1 minus 3, and again here we get hard limb, this is 2 times 0 plus uh, the, so as my mistake, we need this to be 0 1 and 0, not 0 1, so this has to be 1 0 because we are talking about P3, and so this is 2 times 1 plus 2 times 0 minus 3, and so again here as well what we get is this becomes 0, so 2 minus 3 is minus 1, and so again for the class A, uh, the value for A we get 0, which is the negative class. And finally we look at the value for the data point A4, and so this one A is equal to hard limb, and here we have 2 2, and at the data point P4 has coordinates 1 1, and then we do plus minus 3, so we get hard limb, and this is 2 plus 2 times 1 is 2, and again 2 times 1 is 2 minus 3, and so we are looking at the value of 4 minus 3, which is 1, and so that value is greater than or equal to 0, and so this time the value of a is 1, which makes sense because now this is on the other side of this decision boundary that we have, and therefore that it gets classified as the positive class. So again, just to recap, this particular decision boundary that we have right here has was created using the values of the 2 2 for w, which is this one, 2 2 for w, and minus 3. So if I were to write that again, we would simply write in terms of p1 p2, we could say p1 p2 minus 3 is equal to 0, so that's 2 times p1 plus 2 times p2 minus 3 is equal to 0, or in xy terms we could write 2 times let's say x1 plus 2 times or 2 times x plus 2 times y minus 3 is equal to 0. So that is essentially our decision boundary.